Hi, in this e-lecture, we're going to be focusing on this topic called scheduling. Okay, so before we go into scheduling, let's just quickly recap on the state transition diagram. So if you remember what we discussed, we said that whenever we create a new task, it goes from the new to the ready state by default. Okay, and what happens is at any point of times you can have many tasks in the ready state. So you can have up to n number of tasks in the ready state, but only one task can be chosen to run and make use of the CPU. And the responsibility of who gets selected lies with this very important person called the scheduler. Okay, so this scheduler is part of the OS kernel, and this scheduler will decide who should be scheduled to run. Okay, so there are many different scheduling algorithms. Okay, of course we say that for RTOS environment, we say that the selection is based on this important thing called priority. Okay, but in this lecture slides, we're going to be exploring uh, scheduling algorithms in general. Okay, and trying to understand better how OS scheduler is actually designed and how different types of schedulers may behave. Okay, so what exactly is a scheduling algorithm? It is basically a algorithm that has a set of rules, okay, for allocating tasks to the processors. Okay, why we say processors is because in some architectures you may have multi-core systems. Okay, so you may have multiple cores running code concurrently. Okay, so that is of course more complex. Okay, but in our situation we are dealing with a single core, a single processor, and many tasks are waiting, okay, to get a chance to run on this processor. Okay, and what is important is we want to be able to meet all the deadlines. Okay, so you can have multiple tasks, each with different deadlines, and we want to be able to fulfill all these deadlines. Okay, and how do we come up with a scheduling algorithm that is able to fulfill this objective? Okay, so let's look at a simple example to get started. So we have three tasks here: task A, B, and C, and each of them have their own execution time and a deadline. Okay, now let's uh, analyze this, okay, from the idea that all the tasks are ready at time t0. Okay, what does this mean? That means at a particular time instance t equals 0, okay, which is this line here, all the tasks are ready. Okay, so many tasks can be ready, but only one of them will be selected to run. So let's look what would happen if I use this scheduling algorithm where I schedule A first, followed by B, and then C. Okay, and we say that no preemptions. No preemptions means once a task is uh, switched to the run state, it will run until it completes. Okay, that means it fully completes whatever execution time it needs, and then the next task will get a chance to run. Okay, so that is what we mean by no preemptions. Now in this sequence A, B, and C, A will run. A requires only 10 milliseconds of execution time, so each bar here is each bar here is equivalent to 10 milliseconds of execution time. Okay, so once it completes, okay, B can run. So B will take 20 milliseconds, followed by C, 30 milliseconds. Now let's examine the deadlines. Okay, we see that deadline for B was actually 20 milliseconds. Okay, execution time is 20 milliseconds, and deadline is also 20 milliseconds. Okay, but since we scheduled A first, okay, to run, by the time B started to run, it would have missed its deadline over here. Okay, it would have missed its deadline. A and C, no problem. A and C are still complete within the deadline specified. Okay, so with this scheduling algorithm, B will miss the deadline. Okay, now let's look at another example where I schedule B to run first, followed by A and C. Okay, so in this scenario, B takes 20 milliseconds, followed by A, then followed by C. Yeah? So I'm following this sequence here: B, A, and C. Now, let's look back at the deadlines. What do you see? Deadline for B is met, deadline for A is met, and deadline for C is also met. Okay, so all three tasks can schedule within their deadlines. Okay, so no problem. Okay, now let's try to change it again. Now we schedule them as B, C, and then A. So what's going to happen? Okay, B gets to execute first, 20 milliseconds, followed by C, and then finally A. And if you look at the deadlines, you see that the deadline for A has been missed, okay, because A only starts over here. Okay, so you can see that with just three different tasks with different execution time and deadline, the way we order the tasks, okay, can have an impact on whether we are able to fulfill the deadline. Okay, so definitely these few slides we are just trying, okay, some combination, okay, but there has to be a better way, a more systematic way of designing an algorithm where all the tasks, the deadline can be met. Okay, so that is what we're going to be exploring in this lecture. Okay, so in this lecture slides, okay, you will be making some assumptions of the behavior of tasks, okay, which may not always be the case in a real time in a real life scenario, okay, but for analysis we make some assumptions. So firstly, we say that tasks are periodic with known periods, okay, known periods P, and the periods do not change with time. Okay, so once I say this task 1, for example, repeats every 10 milliseconds, it will always repeat every 10 milliseconds, and each time it repeats, okay, there can be an infinite sequence of instances. Okay, so what do you mean by that? If you look at the time duration here, okay, for each of this instance, it is different. Okay, and why is it so? It could be very much related to how or what kind of data the task is dealing with at each instance of time. Okay, and at the beginning of the period, okay, the task is released, that means it becomes ready. Okay, so these are some of the assumptions we are making. Okay, now some terminology. One of the things about task is we must know this parameter called worst case execution time, C, and this is basically the amount of time it takes to complete the task without having any form of preemption or interference. Okay, so this of course could vary because the amount of data that I deal with can be different. Okay, take for example a sorting algorithm. Sorting algorithm, if the data is small, I can complete it very fast. If the data is large, I can take a longer amount of time. Okay, so the worst case execution time depends on the how the code is written for the particular task, as well as the amount of the upper bound on the amount of data that I'm going to deal with. Okay, so that is the worst case execution time, okay, for the task. And every task, since it's periodic in nature, uh, in general most tasks have a deadline, okay, and deadline is basically the absolute max time by which I must complete the task. Okay, and definitely the execution time must be less than the deadline, and the deadline must also be less than the period. Okay, and in our case, since we say that the tasks are periodic, okay, we can sort of conclude that the deadline is also equivalent to the period, okay, because the period is the next iteration of the task. So before the next iteration starts, I must make sure I finish the current iteration of the task. Okay, so that is basically why we say deadline is equal to the period. Okay, and all tasks have a hard deadline. That means I have to make sure that I finish everything I need to finish before the completion of the period time frame. Okay, some of the other additional assumptions. Tasks are completely independent of each other. Okay, so once a task period comes around, we say that it automatically goes to the ready state. Okay, and we also do not factor any overheads due to context switching. Okay, again, these are just some assumptions. In reality, especially in your project, for example, there is a lot of dependency between tasks. Okay, because for example, you do not start moving your motors, okay, until data comes in on the serial port, correct? So there is a dependency. Okay, you're not going to move motors periodically just because the system has started, so you have to wait, correct? So there is some dependency, okay, between tasks in a real life scenario, but in our analysis we are making these assumptions. Okay, so just now we talked about worst case execution time. Okay, that means the maximum time required to complete any instance of the task without any interference. Okay, that means there is no sort of preemption by this task by another task. Okay, the worst case response time is the maximum time that you can have, okay, taking into account any form of interference or preemption by other higher priority tasks. Okay, so that is your worst case response time. So definitely C has to be lesser than or equal to R, and R has to be lesser than or equal to D. Okay, so I think this is quite clear. This is without any preemption. Okay, just as it is. This is with preemption, and this is your periodic deadline, D. Okay, so roughly you can get the idea why C has to be less than equal to R, which has to be less than equals to D. And in our case, we say that D is equals to P, your period. Now, just to illustrate the difference between worst case execution time and worst case response time, in this first case, worst case execution time, you see that there is no interference. At each instance, the task, the moment it starts running, it is allowed to carry on until it completes running. Okay, so what is the worst case execution time depends on maybe the bound of the data size or the complexity of the algorithm, okay, in dealing with different type of data. For worst case response time, we are looking at a task that can be preempted by another task, and so the total time that the task takes before it can complete is now longer. Okay, so that's the worst case response time. Okay, as can be seen over here. Now where task X is preempting task 1, and so the entire execution time for task 1 in that instance is now going to be longer. So what is the impact? As you can see here, if a task that is coming in to preempt my current task is going to go for a significant amount of time, then my task that I'm supposed to be executing will get delayed further, and eventually it could lead to a scenario where I miss the deadline. Okay, so your task that is coming in, okay, to preempt the current task can cause the task to miss its deadline. So that is a important issue, and that is the nature of a real-time system, because in a real-time system we say that priority is the basis by which you will preempt a lower priority task to allow a higher priority task to run. Okay, so when a lower priority task is running, a higher priority task that becomes ready can preempt it. Okay, which means that the way we assign priorities is not important, correct? Because that will determine whether a lower priority task actually gets to run to completion, or is it always going to be preempted by a higher priority task. Now let's look at this scenario here. I have three tasks, okay, T1, T2 and T3, okay, and the highest priority task is T1 followed by T2 followed by T3. So in this example, the tasks are not all ready together at t equals 0. At t equals 0, you only have T2 which is ready. Okay, so the other tasks are not yet ready. Only T2 is ready at time t equals to 0. So T2 will get to run, and at some point of time T1 will become ready. So when T1 becomes ready, what happens is at that point of time there will be a preemption, okay, and you will switch over to T1. Okay, the higher priority task you will switch over, and T1 will get to run until some point of time, whether it either it completes or it goes to some block state, and then eventually T2 can carry on. Okay, but before that, while T1 is running, even if T3 becomes ready, T3 is considered a low priority task, so it will still have to be waiting in the ready queue. Okay, so you have to remember that at this point of time when T1 takes over, if you look at your ready queue, okay, what you see is you will see that T2 is already there. Okay, and then over at this point of time, what happens? T3 joins the queue. Okay, and T3 joins the queue behind because T3 is lower priority. Okay, of course, if it was the same priority, then it will still be scheduled after T2 because T2 became ready first. Okay, so T3 is now coming after T2, so T2 will have to complete after T1 gives up the CPU. So at this point of time, of course, it's not clear. In this example, we're not too concerned about what is happening. Either T1 has already completed the task fully, or T1 has given up the CPU, or because it has gone to a block state. Okay, in either situation, T1 is no longer in the running state, so T2 can take over the CPU. So T2 is going to run, and when T2 completes, okay, again either it completes or it gets blocked, then eventually T3 is able to run. Okay, so this is basically how a preemptive priority driven system will be running. Okay, very similar to what we are also going to be seeing for our project and our labs. Okay, because RTX RTOS also has behaves in the same way, preemptive priority driven scheduling. Now let's look at this preemptive priority driven scheduling approach. And what do you see as important? The important thing is actually priority, correct? Because context switching is happening based on priority. So how do we assign priorities to tasks? Okay, so there are two mechanisms. One is either fixed priority, or we can go with dynamic priority. In fixed priority systems, once I set the priority, which is done when I create the task. Okay, so if you remember in our last tutorial 4, I mentioned that when we call OS thread new, okay, there is one of the parameters is called attributes. Okay, and attributes has a few, again, sub parameters, and one of it is priority. Okay, so we will be looking at that, okay, in the lab exercises to give you the idea on how we can actually change priorities in our system. Okay, so generally when we create a task, we will set a priority, and that priority is fixed while the system is running. But some OS also has this capability of a dynamic priority system, where the priority is changed, okay, during runtime. Generally this change is temporary. Okay, we will cover that in a later lecture. But dynamic priority, dynamic priority has two types. Okay, we will be covering one of it in this lecture, which is just to give you an idea how scheduling algorithms can also switch around, okay, priority. We'll also cover a situation where uh, a task may be blocked for too long over time, and then we want to initiate some priority switching mechanism. Okay, that we will cover in another lecture. Okay, so one of the most common algorithms for scheduling is what we call the RMS algorithm, rate monotonic scheduling, by Liu and Leland. As you can see, it's very old algorithm, but still it is used very widely today because it forms a baseline from where we can actually decide priorities of tasks. And one of the key principle is priority is inversely proportional to task period. Okay, so it does not depend on the execution time, it just depends on the period. And the thinking behind it is quite straightforward. If I have a task that requires frequent attention, okay, that means I need to keep on running it very regularly, then I should schedule it to have a higher priority so that the CPU is able to handle the request by this task. Okay, so it's a very simple thinking process. Priority is inversely proportional to task period. The shorter the task period, or in other words, the higher the task frequency, the higher the priority. Now let's look at this example here. So I have three tasks, task 1, task 2, and task 3 over here, with different computation time and different deadline. Okay, so now what is going to happen if all the tasks, so let's look at the priority first. Okay, so since we know that we are using RMS, the one with the smallest period, which is task 2, is priority 1, followed by task 1 is priority 2, followed by task 3, which is priority 3. Okay, and all tasks are ready at time t equals to 0. So what is first going to happen? So the task with the highest priority, which is T2, is going to get a chance to run first. Okay, so T2 will run, and after T2 runs, and T2 only takes computation time of 1 unit. Okay, and since all three tasks are ready, after T2 runs, I can immediately switch over to T1. Okay, and T1 takes 2 units, and after that, what happens? Okay, task 2 only repeats every 4 units of time. Okay, and task 1 only repeats every 5 units of time. So at this point of time, at time 3, what do you see? You see that task 1 also doesn't need the processor, task 2 also doesn't need the processor. So what happens is you have some time for task 3. So task 3 gets to run. Task 3 requires 2 units of time, but after completing 1 unit of time, the next periodic interval of task 2 happens over here, right? Because task 2 repeats itself every 4 units of time. So at this point of time, your task 2 will get a chance to run. Okay, so there is a preemption over here. Okay, task 3 gets preempted and task 2 gets to run. And then what happens? Okay, task 2 only requires 1 computation unit. So the moment task 2 finishes, okay, the next periodic interval of task 1 triggers. So task 1 has takes 2 units of time. And again, what do you see? Okay, so this is 7. At time 7 to 8, you have 1 gap, 1 unit time gap where nobody wants the processor. And so task 3 is able to resume. Okay, task 3 is able to resume and it's carrying on. Now after that, again task 2's periodic interval triggers again. So it takes 1 unit of time followed by 2 units for task 1 from the time of 10 onwards when is the next periodic interval. Okay, and then again at time T12, T2 has another round of its periodic interval. Okay, and then from this period of time 13, okay, all the way to 15 here, there is again nobody requesting the CPU, so it's actually not being utilized over here. Same thing. Okay, over here as well, 9 to 10, also nobody being utilizing it. So at time T15, T1 launches, but task 1 requires 2 units of time to complete. Okay, but what happens before you can complete, the next iteration of T2 comes in, and T2 is higher priority than T1. So what will happen is we have a preemption over here. Okay, and T2 will get to run for 1 unit of time before you get to switch back. Before you get to switch back to T1. Okay, and after that again you have a period of time where nobody is using. So this is 70. So this is 18 to 20. Nobody is using it, and again in 20 you have the next iteration of the T2. Okay, and then you start again, and again T3 comes in. Okay, so T3, T2, T1, if you notice, all of them will trigger again exactly at t equals to 20. Okay, at t equals 20 is the time where it is exactly the same as t equals 0, because all three tasks are ready together at the same time at t equals 20. Okay, and if you notice here, this behavior is exactly what is repeating itself over here. Okay, so this basically leads us to the next important aspect, which is called the hyper period. Okay, so for the hyper period, you will notice that, okay, when I look at the entire hyper period, subsequently the behavior of the task repeat themselves exactly as to how they were during the hyper period. Okay, so this hyper period is basically known as the least common multiple of the task periods. Okay, so how the context switching happened between these three tasks, okay, during this hyper period is exactly how it will repeat again. So every 20 units of time, so 20 to 40, you will see the exact same behavior. Okay, similarly 40 to 60, you see the exact same behavior. Okay, so once you are able to look at a hyper period of a task schedule analysis, you can say for sure that this is exactly how it will repeat itself again and again for every hyper period. Okay, and how do you calculate this hyper period? You look at the least common multiple of the task periods. Okay, so in this case we have task periods of 4, 5 and 10. So the least common multiple is 20. Okay, so the schedule repeats itself every hyperperiod. Okay, and why is this hyperperiod important? Because of this. If I'm able to analyze the behavior over the hyperperiod and no deadline is missed, if within the hyperperiod no deadline is missed, then you can say that the task is schedulable because the hyperperiod is what repeats itself again and again. So within the hyperperiod, if I'm safe, okay, I do not miss any deadline, then I can say that the task set that you have is schedulable. Okay, so that is important. So what is this schedulability analysis? Okay, so a feasible schedule is one where all the timing constraints that can be met. And what we want is we want to come up with the optimal scheduling algorithm that can produce a feasible schedule given the current task set. Okay, so a task set is basically a group of tasks with specific computation times and specific deadlines. Okay, and what we want to do is we want to see if I can come up with a scheduling algorithm that eventually translates to a feasible schedule. That means I can meet all the timing constraints. Okay, so for RMS, what is known is if I can just arbitrarily use a fixed priority assignment, okay, with the current task set that I have. Okay, now if I have n tasks, I have a total of n factorial permutations of priority assignments. Okay, so given these three tasks, T1, T2 and T3, okay, if I try to just randomly allocate them to different levels of priority and I just try it out and analyze the behavior. If I do this and I'm able to get, okay, at least one of them or more of them to be schedulable, okay, then we can say that one of them will definitely be RMS. Okay, so let me repeat that. If I just randomly assign priorities to the task and out of them, okay, so in this situation, this option and this option produce schedules that are feasible. Okay, that means the priority assignments are feasible. That means I do not miss any deadline. That means what I'm saying is that at least one of them would be RMS. One of them would have been RMS. Okay, so why this is important is instead of doing all this trial and error and guesswork, I can guarantee that if I use RMS and I can find a schedulable algorithm, then definitely you will have a feasible schedule that you can apply to your system. Okay, so the whole idea of schedulability analysis is to analyze the system and to predict its worst case behavior, okay, with respect to the timing that you have. Okay, and trying to see whether this worst case behavior meets whatever timing constraints that you currently have imposed on the system. Okay, and how do I analyze schedulability? Okay, so that is basically what is you can compute what is known as the utilization of a periodic task set. Okay, so what is utilization? Utilization is basically giving us an idea of how much of the processor's time is spent in executing each of the individual tasks. Okay, so let's say I have these three tasks and each of these tasks have specific computation times and periods. Now, the utilization is basically taking the computation time divided by the period for each of the tasks. Okay, so 2 divided by 5, 1 divided by 4, 2 divided by 20, add up everything. And the condition says that utilization must be less than or equal to 1 is a necessary condition. Okay, that means the overall utilization of the CPU must be less than or equal to 1. Okay, this condition, necessary condition, means it must be satisfied. Okay, if I do not satisfy this condition, then you don't need to look any further. You know that you cannot have a feasible schedule no matter what. Okay, this is very important. Utilization must be less than or equal to 1 is a necessary condition. But necessary means it is not sufficient. Okay, it is not sufficient. Okay, not sufficient means what? That means Even if I fulfill this criteria, doesn't mean it is guaranteed to be schedulable. Okay, doesn't mean it's guaranteed to be schedulable. I can have situations where I fulfill this criteria where u is less than or equal to 1, but yet it is still not schedulable. Okay, let's look at this scenario here. Okay, looking at these two tasks here, T1 and T2. Okay, given this execution time and this period. Okay, if I were to calculate the utilization based on the formula, so 2 by 5 plus 4 by 7, I will get 34 or 35, which is less than or equal to 1. Okay, so the utilization criteria is satisfied. But what do you see? If I try to schedule T1 first, okay, followed by T2. So after T1, I get to run T2, but T2 requires 4 units of time. Okay, so since T1 is considered higher priority in this case, I'll switch back to T1, and after T1 then I can carry on with T2, and what happens is I miss T2's deadline. Okay, because T2's deadline is 7. Okay, by the time I complete this, it's already 7. So this is the 7th unit of time, but I haven't completed my T2. Okay, so in this situation, T1 is higher priority and T2 misses the deadline. What if I switch it around? Okay, and I say T2 is higher priority. So T2 runs first, followed by T1, but T1 runs, okay, and after T1 runs, what do you see? T1's deadline was 5 units of time. Okay, so this was the 5th unit of time, and at that instance of time, I only completed half of T1. Correct? Okay, so you can see that in this situation, no matter I try to put T1 as higher priority or put T2 as higher priority, it doesn't seem to fulfill both the deadlines that I have, even though the utilization that I calculate is less than or equal to 1. Okay, so this is why we say that, okay, this condition that u must be less than or equal to 1 is necessary but not sufficient. Okay, that means it is important that I have it. I must have it, but it is not enough. Okay, I still need to do other things. It's not enough. Okay, so that is what we're saying here. So how can I proceed? What is the next step? So the first step is I check that utilization is less than or equal to 1, and then I try to assign priorities according to RMS. Okay, and then look at the hyper period. If within the hyper period there is no deadline that is missed, then we say that it is schedulable. Okay, if not, it is not schedulable with a fixed priority scheme. Okay, so that is what we can conclude. Okay, so let's look back at this. So if I look back at this idea now, you can see that based on the periods, task 1 has to be higher priority, correct? Because task 1 period is 5. So task 1 will be scheduled first, followed by task 2, and at that point of time, when task 1's period is up, I will preempt task 2. Okay, so this is a preemption over here. Okay, and then I will run task 1 again, and then followed by task 2, but task 2 misses the deadline. Okay, so task 2 misses the deadline even though utilization is less than or equal to 1, and I follow RMS, correct? So once I see this, I can say for a fact that task set is not schedulable using fixed priority. Okay, so using a fixed priority scheme, this task set is not schedulable. Okay, so that is one thing I conclude. Okay, if we follow these steps by calculating u and then assigning priorities based on RMS and then looking at the hyper period. Now, another condition which is sufficient but not necessary is utilization bound. Okay, sufficient again means what? Sufficient means if I can fulfill this criteria, I don't need to look at other things. Okay, but it's not necessary because again, I may be in a situation where I do not fulfill this utilization bound, but I'm still schedulable. Okay, so the utilization bound is given by this formula. Okay, and it is important to know that it's not necessary but it's sufficient. That means if I fulfill this, it is definitely schedulable. Okay, but it is not necessary. So I can have a situation where I'm still schedulable but the utilization bound is not satisfied. Okay, so this n is basically the number of tasks. So these numbers here are fixed. Okay, so the bound here, b is the bound. So the bound is a fixed number for the number of tasks that I have. Okay, so b2, b5 and b8, all this is the number of tasks that I have in my system, okay, with fixed priorities. Now let's see how we can apply this. Yeah, now let's look at this scenario here where I have two tasks, T1 and T2, both with computation time 1 and one with the period of 2, the other with the period of 3. Okay, so based on RMS, we know that task 1 is supposed to be scheduled with a higher priority. So task 1 run first, okay, and task 1 repeats every 2 units. So every 2 units it repeats itself, and task 2 repeats itself every 3 units. So, and both take only 1 unit of time. So once task 1 does, okay, so at this time t equals to 0, both tasks are ready. So after task 1 completes, task 2 get a chance to run, and once task 2 completes, task 1 is going to launch its next iteration, the next period. So task 1 again runs, and over here what do you see? Task 3 is being task 2 is being having a second initiation of the period. So at that point of time, task 1 is already completed, so task 2 is able to run. And again, in the next instance, task 1 is having the next iteration of its period, okay, and task 2 will only need to run again over here, T2, okay, the next time that task 2 runs, okay, because the period is 3. Okay, so there is actually one empty slot here before the next iteration of task 2, okay, and task 1. But when task 2 and task 1 come together over here, so at this point of time, both task 1 and task 2 will come. Okay, so task 1 will also come here, and task 2 will also come. And what you will see is it will actually be the same scenario as over here. Correct? So this is basically the hyper period. Okay, so you can see that within the hyper period, it is schedulable. Okay, and the utilization, okay, if I calculate the utilization, is actually greater than the utilization bound. Okay, this utilization is basically 1 over 2 plus 1 over 3. Okay, that is the utilization, and it's bigger than the bound. Okay, the bound here is given based on 2 tasks. Since you have 2 tasks in the system, the bound is 0.828. So this is an example of how the utilization that you're going to calculate is bigger than the bound. Okay, but yet it is still RMS schedulable. Okay, so that's why it's important to know what is necessary and what is sufficient. Okay, so when you say necessary means utilization must be less than or equal to 1, correct, but it's not sufficient. Okay, and that is where the utilization bound comes in. As long as the utilization is less than the utilization bound, then it is sufficient, but even if it is not, it may still be schedulable. So this sort of summarizes it. Okay, if my utilization is less than the utilization bound, it is sufficient. Okay, that means it is definitely schedulable. Okay, but if it's less than or equals to 1, it's necessary, but may or may not be. Okay, may or may not be. As long as the utilization is greater than 1, definitely it is not schedulable. Okay, so that is the sort of summary of the schedulability analysis. Now let's come back to this rate monotonic analysis, RMA analysis. So this analysis is for tasks set that meet the necessary condition, okay, but not the sufficient condition. Okay, so necessary means you definitely need it, okay, but you do not meet the sufficient condition, which is the bound. Okay, now let's look at this example here. I have 3 tasks, T1, T2 and T3. Okay, so the utilization, okay, if I calculate this, is given by 0.952. Okay, so I fulfill the necessary condition, which is the utilization must be less than or equal to 1, but I do not fulfill the sufficient condition. The sufficient condition is it must be lesser than or equal to the utilization bound. Okay, the bound for 3 tasks, okay, all these are fixed numbers, is given as 0.779, and it does not meet the sufficient condition. So what can I do? So let's analyze it step by step, one task at a time. If I just have only T1 in my system, the task with the highest priority, then I can see that the utilization is less than the utilization bound. Okay, so T1 alone, no problem, is schedulable. If I include T1 and T2, okay, the highest priority followed by the medium priority, again the utilization is less than the bound, B2. So again, I can pass the utilization bound test. But the moment I include all three tasks, okay, I include all three tasks, what happens? I can see that I fail the utilization test. But again, you have to remember that the utilization bound is a sufficient condition, but not necessary. Okay, that means I may still be schedulable even though I fail this test. Okay, so to understand this better, we need to look at this idea of a critical instance. Okay, what is the critical instance? A critical instance for a task occurs when the task is released. And when you say a task is released, we say that it becomes ready. It goes to the ready state. Simultaneously, when all the other higher priority tasks also become ready. Okay, so we understand that since it's a priority driven system, when all the other higher priority tasks also become ready, then they have to run first before the lowest priority task can get a chance to run. Okay, so that is what we call the critical instance. Okay, and each of these higher priority tasks also have its own periodic intervals, okay, which we need to factor in. Correct. So let's look at how we can understand this better. Okay, so in this example over here, I have three tasks. Okay, task 1, task 2, task 3. Task 1 has a period of 100, task 2 has a period of 150, and task 3 has a period of 350. Okay, and the critical instance that we want to know is for task 3, the lowest priority task. Okay, whether task 3 will be able to fulfill its timing constraints. Okay, so what we want to do is we want to make sure that the worst case response time for tasks, in our case task 3, is such that, okay, I must factor in, okay, all the maximum number of task instances that may interfere with the deadline of the task. Okay, so what do I mean by interference? Okay, interfere. This means all the periodic intervals. Okay, periodic intervals of the earlier tasks. Okay, how frequently they're going to come, how much time they're going to take, and how is it going to interfere with the current computation time of the task that I have. And I have to make sure that all of it is lesser than the deadline. Okay, so if I come back to this here, you can see that P1 has a certain period, P2 has a certain period, P3 has a certain period. And each time they are released, they consume some CPU time. So I need to factor all of that time and to see whether task 4 here can still complete everything before the deadline. Okay, before the deadline. So that is what the critical instance analysis is all about. Trying to understand what is the worst case scenario. That means I have a low priority task that is being released, that means it's getting ready, but at the same time I have a lot of other higher priority tasks that are also getting ready, and all of them are going to take the CPU first. Okay, and they have some periodic intervals. So all of that instances where they are being launched and consuming CPU time, that is the interference. So that together with the computation time of the lowest priority task, uh, factoring all of that into account, can I still fulfill the deadline of the lowest priority task? Now let's look at this timing again. So these are the instances where your tasks are released. Okay, but let's look at the timing a bit better now with this. Okay, so we know that we are interested in the response time computation of T3 at this critical instance, and we know that T1 and T2 are higher priority than T3. Correct? So T1 and T2 will have how many instances? So if I look at it, this is T equals to 0. So this is one instance, this is one instance. Correct? At T equals to 100, okay, I have another instance here. T equals to 200, I have another instance here. And T equals to 300, I have another instance here. Okay, for task 2 is 150. So when it's 150, I got another instance. And when it's 300, I got another instance. Okay, so these are the periodic instances of the higher priority tasks that are happening within the deadline of 350 of the lowest priority task. Okay, so now what's going to happen? So task 1 is being instantiated 4 times. Task 2 is 3 times. So the total amount of time is 280. Okay, plus the computation. So this is the C and this is the interference, correct? C100 is the computation time that task 3 actually requires. Okay, so that computation time taking into account all the interference. So the interference is all the higher priority tasks and all their periodic releases. Okay, so all of that now adds up to 380, which is greater than the deadline or the period of T3. Okay, so if I look at this number, what do I see? I feel that it is not schedulable, correct? But is that really the case? Okay, let's take a closer look at the timing, okay, to understand what is really happening. Now, task 1, again the highest priority, okay, so it's going to run for 40 units of time. Okay, so after that, immediately task 2 will get a run, it's going to run for 40 units of time. And what happens? At this point of time, from 80 to 100, the CPU is free. Correct, the CPU is free. So I can actually go and run my task 3 over here. But of course, I only can run for 20 units of time before the next periodic interval of task 1 kicks in. Okay, so again, I go to 140. Okay, then after 140, what happens? This is only, task 2 is only repeating at 150 units of time. So there is another 10 units of time gap over here for task 3 to do some work. And here will be again 190, and then the next interval of task 1 is at 200. Correct? So at this point of time, there's again another 10 units of time. Okay, and task 1 will finish at 240, and what will happen? Okay, task 2 will only become ready over here, okay, when it's 300. Okay, and until then, okay, until this whole duration of time, the CPU is free. So this 60 units of time is available for task 3 to finish. So 16 plus 10 plus 10 plus 20 is 100 units of time. Okay, so I can actually complete the entire task 3 within the a time of 300 units of time, much earlier than the 350 deadline. Correct? But yet in the earlier analysis, we computed it as 380. Correct? So if we look back here, we computed it as 380. But when I try to dig deeper into the actual timing gaps that I have, I can see that I can actually squeeze in task 3 and complete it within 300 units of time. Okay, so how do we now account for this, okay, in our analysis? Okay, so the problem with the current way of approach is we are looking at only the deadline of 350, okay, and trying to see how many instances of the lower task have already been launched. Okay, so at the time 350, which is the deadline of task 3, okay, what we see is we are looking at how many times that task 1 and task 2 have already been launched. Okay, but if we saw earlier, we saw that by this time instance 300, we are already done. Task 3 is already done. But at time 300, you also launch another instance of task 1 and task 2. That is why when you look at 350, you feel that you don't have enough time. Okay, so the way we need to go about doing this, we need to check at more points. And which are the more points? We need to check at all the periodic intervals of all the higher priority tasks to see whether the lower priority task computation needs have already been fulfilled. Okay, so what we need to do is we need to look at 100 and 200, which is the multiple of task 1, 150 and 300 multiple of task 2, and 350, which is a multiple of task 3. So we need to look at each periodic interval and see if the demand is lesser than or equal to the capacity. The demand is the computation time required by all the tasks that have already been launched, Okay, capacity is the amount of time that's already elapsed. Okay, so if I look at time t1, what do you see? At time t equals 100, you have launched t1, t2 and t3. Okay, this is the task 1, task 2 and task 3. So total computation time is 180, but you have only passed the 100 time mark. Okay, so the demand is higher than the capacity. At time t equals 150, what has happened? Another instance of t1 is already launched, correct? Okay, and you still are running your t2 followed by t3. Okay, at time equals to 200, what happens? Okay, another instance of t1, another instance of t2 has already been launched. Okay, and what you still have t3. Okay, so 260 is still greater than 200. At time equals to 300, what do you see? You have 3 instances of t1 already launched, 2 instances of t2 already launched, and 1 instance of t3 already launched, and the total time is 300, which is exactly 300, the exact deadline. So task 3 is actually schedulable at time 3 t equals to 300. Okay, the issue with the earlier approach is we looked at a particular instance of time and all the tasks that were already launched. Okay, and at t1 and t2 had already launched one extra time over that, so that is why it seemed as if it was not possible, but actually within 300. Okay, if we don't need to factor in the t1 and t2 are launching at 300, but within 300 it is possible that t3 has already completed all the computation it needs. Okay, so to do that, okay, we need to do one more computation, a calculation which is known as the necessary and sufficient condition. Okay, now this necessary and sufficient condition, this is the formula. Okay, I will not go through the details of the formula, but if you look at it from the application perspective, it is very easy. All we are doing is we are looking at the computation time. Okay, and we are looking at the time, okay, with respect to the periodic intervals, okay, of all the lower priority or the periodic intervals of all the higher priority tasks in the system. Okay, so that is what we are trying to do. So let's look at the example over here. So this is how to calculate the various pi over pj over here for the k values. Okay, and the k values are the ones that are used over here. Okay, t equals to k pj. Now again, if you look at the example, it's very easy to relate all these formulas to. Okay, so if I want to look at time t equals to 300, okay, so don't worry too much about all these earlier derivations, as long as we know how to apply it. Okay, so the t equals to 300 is the time that we're interested in, and what do? We look at all the periods of the lower priority, we look at all the periods of the higher priority tasks in the system. Okay, and for each of the tasks, look at the computation time. So this is the task 1, this is for task 2, and this is for task 3. Okay, and we see that the total w that we get is 300. So this shows us that the amount of computation time that is needed at time 300 is exactly the amount of computation time that is available. Okay, so the demand is equal to the capacity exactly at time t equals 300, so we are able to fulfill the requirements. Okay, so again, these two slides are just giving you all the details mathematically. Okay, but if you just understand it from an application perspective, is good enough. Okay, so basically what you're doing is we can take t to be any number. Okay, we can take t to be any number, and at any number we take the computation time of each task, multiply by that time divided by the period of that particular task. Okay, so what we're trying to do is we're trying to see the number of instances that task has already been launched, okay, within the system, and from there we will be able to know whether we are able to fulfill the timing requirements, okay, at any point of time. Okay, now all the while we'll be looking at a fixed priority scheduling system. Now this last few slides is just to explore this idea of a dynamic priority scheduling scheme, where the priority of a task is continuously being changed, okay, during runtime. Okay, and the whole strategy is to do this where the task with the earliest deadline has the highest priority. Okay, so you can have many tasks, and among all the tasks we will choose the task with the earliest deadline to have the highest priority. Okay, and task priority may be updated only when any new task instance is released. Okay, so let's look at what is happening. So we have two tasks here, T1 and T2. Okay, and looking at T1 and T2, we can see that T1 has a earlier deadline of 4. Okay, so that will by default start off with a higher priority. So when task 1 runs, it will take 2 units of time. Okay, after that what will happen is task 2 will get a chance to run. When task 2 is running, okay, so you can see that both of the tasks were released here at time t equals to 0. Okay, and task 1 has a deadline every 4 units of time. Okay, so that is what is shown here, whereas task 2 has a deadline every 10 units of time. Okay, now when task 2 gets to run, task 2 will run for 2 units of time, and then what will happen? Okay, at this instance of time t equals to 4, task 1 will have another iteration, correct, of its period. Okay, and since task 1's deadline here is going to come before task 2's deadline, task 1 will have a higher priority, so I will preempt task 2 to run first. After task 1 runs for 2 units of time, then I will be able to resume back and carry on and finish task 2. Okay, and after task 2, while task 2 is running, okay, actually what is happening is over here at this instance of time, another iteration of task 1 is coming in, correct? Okay, but because task 2's deadline is closer, okay, compared to task 1's deadline for this iteration, then task 2 will be given a higher priority, okay, as shown here, and task 2 will be allowed to carry on, and then task 1 will run. Okay, now when task 1 is running again over here at time t equals to 10, what is happening is another instance of task 2 is launched. Okay, but task 2's deadline is much further away than task 1's deadline, so task 1 is given a higher priority to carry on running. Okay, and after that task 2 will run, and at time t equals to 12, again you see the same thing. There's another instance of t1 coming in over here. So when t1 comes in over here, the deadline for t1 is earlier than the deadline for t2, so another preemption will come in and t1 will run, okay, for another 2 units of time, and after that t2 will be allowed to carry on. Okay, and at this point of time, what do you see? You see that both task 1 and both task 2 have the same amount of deadline, correct? Both task 1 and task 2 have the same amount of deadline. So even though task 1 is again launched over here, task 1 and task 2 have the same amount of deadline, so they both have the same priority. So since they have the same priority, the task that is currently running will be allowed to carry on. Okay, and then I will switch back to T1. Okay, so that is the earliest deadline first scheduling approach. So this is based on a dynamic priority. Okay, so the priority of the task will keep on changing as you are executing the code in the system. Okay, so that is how the EDF works. Okay, and it is an optimal scheduling policy. Okay, and you can say that as long as the utilization is less than or equal to 1, okay, EDF will always produce a feasible schedule. Okay, so for EDF, okay, or any form of dynamic scheduling policy, okay, with that means the priority is dynamic, scheduling is feasible if and only if u is less than or equal to 1. Okay, that means the utilization is less than or equal to 1. So that is a necessary as well as sufficient condition. Okay, so that brings us to the end of this topic on scheduling. Okay, so what we have done is we have looked at the scheduling policy for a system with multitasking. We have looked at RMS, and we have just briefly covered the EDF. Okay, so what we have done is, of course, we have made some assumptions, okay, in terms of the fact that the tasks are periodic, Okay, and they always repeat a specific instance of time, and there is no dependency between one task and another on being ready. Okay, so these are some of the assumptions we have made, which again, like I said earlier, may not apply to a real life scenario, okay, like a project, but it's good, okay, to understand some of these terminologies and techniques, okay, to see how you should actually assign priorities, okay, in a system. Okay, it's not just some guesswork, but you need to do some analysis on timing, computation, the behavior that you expect, okay, and then you assign priorities. Okay, so that brings us to the end of this lecture. Okay, in the next lecture we'll be looking at the concurrency, okay, and how we can synchronize tasks and do data protection, okay, and some other mechanisms. Okay, so thank you.